Hi guys, in this video we will start the level 1 problems based on the EMF and motional EMF. So first of all, there is a right angled triangle ABC you can see, which is made up of metallic wires, and it is moving with a uniform speed of V, and we have to find out the EMF induced in the complete loop ABC as well as in segment BC, in segment AC and in segment AB. So first of all, we can see that this magnetic field is uniform, and therefore if a loop is moving in a uniform magnetic field, then EMF induced in the loop will be 0. We know that, and I will prove this also in the last part of this video. Now in segment BC, so if I draw the segment BC, this is the segment BC, and this is B and this is C, and if I use the Fleming's right hand rule, then I can see that the first finger of my right hand would point in the downward direction because magnetic field is in the downward direction, and the thumb of my right hand would point in the direction of velocity, that is towards the left side. So the second finger is pointing towards the positive terminal of the EMF. Therefore this will be the positive terminal and this will be the negative terminal, and this EMF will be E, and EBC will be equal to BLV, where B is the magnetic field, L is its length, and let's suppose that its length is L, and V is the velocity. Now if I talk about the EMF induced in BA or segment AB, then this is the part D. I am taking the D first. So in segment AB, you can see that EMF induced will be 0 because its length is parallel to velocity. Therefore the EMF induced will be 0. Now in segment AC, we will see that in segment AC is inclined at some angle with the horizontal, and there would be two components of AC. The one component would be like that, and the other component would be like that. So this component will be equal to the length of BC, LBC. You can see that this component will be equal to LBC. And therefore the this rod and this component will be same as that of length of AB, but the EMF induced in component 1 will be 0 because it is its length is parallel to the velocity, because velocity is in this direction, and this length, this one, is parallel to the velocity, and therefore the EMF induced in this component will be 0, and the EMF induced in the component 2, which is this LBC, this one, will be equal to the EMF induced in rod BC. And the polarity of this EMF can be also calculated, that by Fleming's right hand rule, that if you will stretch your first two fingers and thumb of right hand in mutually perpendicular direction, and you will point the first finger inside the plane, as the magnetic field is towards the direction which is inside the plane, and the thumb is pointing towards the velocity, therefore positive terminal would be in the downward direction. So the EMF induced in rod AC will also be like that. So this will be negative and this will be positive. This is E. So if you will combine these batteries as in the loop, so you can see that this cell will have an EMF E, and this cell will have an EMF E, and this will have zero EMF. So if you will apply the Kirchhoff law like that, then you will see that this is plus E and this is minus E will be equal to 0. So EMF induced in the loop will be equal to 0. Now we will move on the next question. In this question, there is a conducting disk of radius r which is rolling purely on a rough horizontal surface, and its center is moving with a constant velocity v. Now its omega will be equal to v by r. Okay, so we have applied a magnetic field pointing inside this plane, and we have to find out the induced EMF between points P and Q, P and C, and Q and C. Now we all know that in pure rolling motion, the point which is touching the ground is at permanent rest, so this velocity of point P will be 0. So we can assume that this disk is in the state of pure rolling about this point, and therefore we can assume a rod which is rotating about this point with the same angular velocity omega. So this is point Q. So the EMF induced between Q and P, VPQ, will be equal to half B omega L square, where the length of this rod will be 2r and omega will be equal to V by r. So VPQ will be equal to 2BVR. Okay, we have replaced omega by V upon r, and this is 4, and 4 will be cancelled out with 2, and remaining will be 2. Now we can see that the direction, that the polarity of this EMF will be in such a way such that if we point the thumb towards the direction of the motion, towards the right side of our right hand, and the first finger towards the magnetic field, then we will see that the positive terminal will be Q and negative will be P. So we can say that VQ minus VP will be equal to 2BVR. Now similarly we can find out the potential EMF between C and P. So by the similar manner, the potential of C will be greater than the potential of P, and the magnitude of this VC minus VP will be half B omega r square, because now the length of the rod will be this is r. Okay, so this will be VC minus VP will be equal to we are replacing omega by V upon r. So this is half BVR. Now if we wish to find out the potential between Q and C, then this is equation 2 and this is equation 1, and subtracting 1 and 2, so we can get 1 minus 2. So VQ minus VC will be equal to 3 by 2 BVR. So this is the potential difference between Q and C. Now we move on the next question. In this question, there is a circuit you can see in the diagram, which is containing a switch and a battery, and the switch is initially open. And there is a square loop which is being placed in the same plane as that of circuit and nearby the circuit, and we have to find out the induced current, direction of induced current in the square loop when firstly the switch is closed and after some time that switch is being opened. Now when as soon as switch is closed, so let us suppose that switch is being closed like that. Okay, so the current will flow in this direction initially, and therefore if you can predict the direction of magnetic field due to this current in this square loop, then you will see that the greatest influence of magnetic field would be due to this wire, because it is closest to the square loop. So the magnetic field due to this wire in this square loop will be in the outward direction. You can predict it by the Fleming's right hand thumb rule. So the magnetic field will be in the outward direction, which means magnetic field will be dot. Okay, and we know that initially switch was open, and as soon as we have closed the switch, the current increases, and therefore this magnetic field increases. So if this magnetic flux increases, then the induced current in the loop will tend to decrease this magnetic flux, and hence the induced current will produce its own magnetic field in the opposite direction of this magnetic field. So it will produce a magnetic field inside the plane, and therefore the current initially would be induced in clockwise sense, so that the magnetic field due to this induced current will be in the cross direction. So initially the current will be in the clockwise sense. Now as soon as you will open the switch again, then this current will decrease in the main circuit. This current will decrease, and therefore this magnetic field which is outside the plane will decrease, and hence the induced current will tend to increase this magnetic field and magnetic flux, and hence it will support this magnetic flux because it is decreasing. I'm again reminding you that the induced current always tends to oppose the change in magnetic flux. Now in this case, in the second case, when we have opened the switch, then the current in the main circuit is decreasing, and hence this flux is decreasing. So the induced current will oppose the change in this flux. Now the change is of decreasing nature, and hence this induced current will oppose this decreasing nature of the flux, and it will support it, and it will try to increase it. So it will create its own magnetic field in the same direction. Therefore now the current will be in anti-clockwise sense. So the correct option will be option number D, which says that initially the current will be in the clockwise sense, and then it would be in anti-clockwise sense. Thank you. In this question, there is a wire arrangement which is in form of a parabola, you can see, whose equation is given by y is equal to kx square. It is this complete wire arrangement is located in a magnetic field which is pointing inside the plane of this arrangement, and at the moment t is equal to 0, a straight rod which is started from this point is moving with a constant acceleration a. It is given in the question, and this rod is at a distance y from this origin at some time t, and we have to find out the magnitude of induced EMF in this rod at this time. So let us suppose that the coordinate of this point is x comma y, therefore this length will be x and this length will be also x. So the length of this rod will be 2x at this instant, and its velocity will be calculated by v square is equal to u square plus 2s. Now v square is equal to u square, which is 0, as initial velocity was 0, plus 2, the acceleration is a and the y coordinate is y, so v will be equal to root of 2ay. So the induced EMF, we can say that it is BLV. So E will be equal to B, and length of this rod will be 2x and its velocity is v. So E will be equal to B into 2x into under root 2ay. Now x, you can see, is y upon k root by this one. So EMF will be equal to B into y under root 8a by k. This is the final answer. Let's move on the next question.